Okay, so today's class activity is going to go over chapter 25, sections 4 through 7, and our concept questions are 7, 8, 9, 10, 7, 8, 9, 10, 11, and 12, and then exercises 16, 35, and 43. So I encourage you to go work on those and then come back and use this video as a guide and some hints and help to check your work. We'll start now with number 7. So go ahead and take a look at number 7. Try to solve that one based on your reading and your preparations. Okay, so what we have is we have a capacitor with a gap of D, and this capacitor has got a gap D, and it's been charged to a potential difference of delta VC. So the potential difference across the capacitor is delta VC. You've charged it, and then you've disconnected it from any batteries or any wires or anything. So it's sitting there all by itself. And then you take some insulating handles and you grab onto it and pull it apart until it's now 2D. Okay. So question is, what did that change? What does using insulated handles mean? And what did changing the gap to 2D do to the charge on the plates, the electric field inside the plates, and the potential difference across the plates? Okay. So first of all, the insulating handles means that no charge can leave. Remember, the Q is confined to the plates. It's physical objects. It's electrons or the bare nuclei that are on this plate. They can't fly away. They can't become fields. They're physical objects. And so by pulling these apart using the insulating handles means that Q is fixed. So Q did not change. Okay, well, what about the electric field? What does electric field depend on for a capacitor? Okay, the electric field is Q over A over epsilon 0. Does that depend on the gap? It doesn't. And so the electric field remains constant as well. Okay, and then finally, what happens to the potential difference across the plates? Well, the potential difference does depend on the gap. So the electric field stayed the same, but if the gap doubled, then the potential difference doubled. Okay, let's take a look at number 8. Go ahead and check that one out. Okay, this might look a little familiar. We did this one, but asked a different question. We have a capacitor with these 5 dots, A, B, C, D, and E. Okay, we have those 5 dots in there. And we want to, in this question, we want to find out what is, or rank the potential, the electric potential at those 5 dots from most positive to most negative. And our diagram shows that the top plate is the negative one, and negatively charged plate, and the bottom is a positively charged plate. So what does potential inside a capacitor depend on? It depends on the electric field and how far away you are from the negative plate. So the gap is D, so the potential difference across the capacitor is E times the total gap. But the potential difference inside the capacitor depends on how far away you are from the negative plate. And so delta V between the negative plate and the point within is equal to E times S, whatever position you're at. So then the potential grows, it increases as you go away, since the electric field is positive there. And so we have this electric field, and it's growing, and S is growing. And so that means, electric field is constant, but S is growing, which means that A and B are the same. So we have VA is equal to VB, and those are greater than VC, which is greater than VD, which is equal to VE. Okay. So the negative plate is the lower, sometimes we call it 0, but it's better to just say it's the lower potential. and the positive plate is the higher potential. And so these are growing in potential towards the positive plate. Okay, now let's move on to number 9. Okay, so 9 is kind of similar. We've got the diagram here. We've got 2 dots, negative positive plate. The first dot's 1 millimeter away. The second dot is 3 millimeters away from the negative plate. So what is the ratio V2 over V1? With this being 2, this being 1. Okay, again, note that this is 3 millimeters away and 1 millimeter away. All right, so, well, V2 is this one. I am 2 units away from the negative plate, so that's going to be E times 2. I'll just do that. And 1 is only 1 millimeter away, so it's E times 1. And because the electric fields are the same, or the electric field is constant everywhere within, that, oh, sorry, that's 3. I apologize. It's position 2, but it's 3 millimeters away. Let me rewrite that. That's kind of ugly. So we get a 3 over 1, and so we get a factor of 3. Okay. Now what can you say about the electric fields? What is E2 over E1? So hopefully you were able to say that E2 over E1 is just 1 because it's constant. And that's what we use to be able to get this ratio, that it's constant within. Okay, let's turn our attention to number 10. Okay, so this is a similar question, only now we have a point charge, okay, and we're measuring 1 millimeter away and 3 millimeters away. We're asking the same question, what is V2 over V1? Well, what does the potential of a point charge depend on? Very good. It depends on the inverse of the position or the distance from the point charge. So it's K Q over R squared. Okay, and so this would be R1 and R2. So in this case, the KQ's cancel, and so I simply end up with an R2 squared over an R1 squared, and R2 is a sorry, I got myself backed up here. Sorry, I wrote this wrong. That's a 2 and a 1. Is it a 1 and a 2? I apologize. I just got my units messed up. So this should be, it's too dirty now. Let me clean that up. This should end up being a KQ over an R2 squared. Sorry, not squared. I apologize. I'm messing this one up. Let me just start all the way over. 10. Okay, so we have 2 points. This is 1 millimeter, 2 millimeters. This is 3 millimeters. This is 0.1 and 0.2. Okay, and so V2 over V1 is what we're looking for, and the equation for a point charge, I'm just going to go ahead and plug in. It's KQ over the distance, just the distance, not squared. And so that's going to be V2 is 3. This is KQ over the distance for V1, which is just 1. Same charges, so we get a 1/3 there. I apologize for my writing mistakes over there. Okay, and then they ask the same question, what is E2 over E1? Well, how is that different? What does E depend on? So E is the same, except for instead of 1 over R, it's 1 over R squared. And so this would be 1 over 9 over 1 over 1, which gives me 1 over 9. Okay. So what's important is recognizing the potential depends on 1 over the distance from the charge. The electric field is 1 over the distance squared. Okay, let's try 11. All right, go ahead and take a look at that one, see if you can do that. Okay, so we've got a point, positive charge, a point, another positive charge, and a point. These are A, B, and C. This is for part A. And the question is to rank them from most positive to most negative for the potentials, the electric potentials. Okay, so where is the potential? Well, first of all, the potentials here, are they positive, negative, or both? We can see that the potentials are going to all be positive because all of my source charges are positive. And so I add up those values, they're all positive. And so when I'm looking at this, where is the potential the biggest then? In the middle, I have, it's close to both of them, and so it's going to add up. I'll get double. Now on A and C, it's close to one, but far from the other, so the contribution from the other gets small. But since it's symmetric, they're going to be the same. So we'd have B is greater than A equals C for the potentials. Now notice, I didn't care about directions because potential is not a vector. If this was asking me for the electric fields at those points, this would be answered completely different. B would be 0 because it care about directions, but potential doesn't. Okay, what about B? We have the same configuration, only a negative charge. This is still A, B, and C. Okay, so what can you say there? Okay, now the middle is 0 because it's the same distance from a positive charge as it is from a negative charge, and since we just add them up, they're going to give opposite values. This will give a positive potential, this will get a negative potential, so it's 0 there. Okay. Now this one is still closer to the positive and far from the negative, so this should be a positive value. And this one is closer to the negative, so this should be a negative value. So going from most positive, we have A is greater than B, which equals 0, and that's greater than C. C is negative, closer to the negative. B is positive, closer to positive, and B is in the middle, so it cancels out. All right, go ahead and now move on to 12. Okay, so this one hopefully looks familiar too. We've done this problem before. Drawing it out carefully. Okay, so we have a charge with 2 units of positive charge at this position and a charge with 1 unit of negative charge at this position. And the question is, draw a dot or dots at the location or locations where the potential is 0. Okay, so what is important here? What are we trying to apply? Okay, now unlike electric fields, I don't care about directions. And so I just care about how big and how far. So this charge is big, and in this region, it's close to this charge. Okay, and since the potential of a point charge depends on the size of the charge and inversely with distance, then this area here will be positive. Because this one is negative but far away, so it can never compensate for the large charge and closeness. Now over here, this area is closer to the negative charge, and so it's going to be a big contribution from the closeness, but it's far from this charge, but this is a bigger charge. So there is a possibility for it to be 0 over here. And in the middle, it's also possible for it to be 0 because, again, if we're close enough to the negative charge, then the distance from the larger charge will compensate from the closeness of the smaller charge. Okay, so with that being in mind, we know it's not over here anywhere. Now the condition is just simply, this is twice as big of a charge, so I need the spot to be twice as far from this one since it is linear. It is linear, as we saw up here. Potential is linear with distance. And so this spot right here, or more so right in between them, that spot is twice as far from the positive as it is from the negative, and the charge is twice as big as the negative, and so we have a 2 over 2 versus a 1 over 1, and so that works. But over here works as well, because that point is 3 units away, 1, 2, 3 units away from the negative charge, and it is 1, 2, 3, 4, 5, 6 units. So it's twice as far from the positive charge as it is from the negative charge. And since the positive charge is twice as big, it compensates. We have twice the big charge as Q, but also twice the distance. So it could be here or here. Okay? All right, very good. Now we're going to move on to the exercises. So go ahead and take a look at 16. All right, so this one we just have to be careful with some of our definitions. Okay, we have a charge that is being an electron that's being slowed down by an electric field. So we have an electron, it's starting here, and then it gets over here. And this is its V0 and it's V1. Right? It's moving this way. That's its velocity, moving that way. All right? But it's slowing down, which means the acceleration is that way. It's opposite. Now let me ask, what is the direction of the electric field in this case? Okay. What do electrons want to do? Do they want to go along with electric fields or away? Okay. They want to go, the electrons want to move against an electric field, or more so, an electric field causes an electron at rest will accelerate against the electric field. And so that means that the electric field is this direction because it's slowing down. It means it wants to accelerate against it. So the acceleration is opposite the direction of the electric field because of forces. Okay. Now let me just give a hint since that's a bit of a review. We have the force is QE. Okay. So if we have a negative charge here, that means the force is opposite the electric field. Our acceleration is this way, which must be opposite the electric field. Okay. All right, now we have a principle about the direction. So the first question of this is, did the electron move into a region of higher potential or lower potential? So how is potential related to electric field? How is the direction of electric field related to gains or losses of potential energy? Think about our capacitor examples that we saw. So potential in a capacitor, we saw, grew from the negative plate. So as you move away from the negative plate or move towards the positive plate, you gain potential. But we also know that electric fields point from positive to negative. Okay? And that's a truth. And so we can use that idea to see that electric fields point towards lower potential. Electric fields point towards lower potential. So I repeated that because that's a really good conceptual check. We know that this is pointing towards lower V, pointing away from high V. And so this electron is moving towards lower V because it's slowing down. Okay, so in part A, it's moving towards lower potential, lower V. All right, well, on B, okay, actually I'm going to move B down here. B says, what is the potential difference that stopped the electron? So what's the potential difference between here and here? So this minus this. So we're going to have B1 and B0. Now notice my velocities, I give a little hook to them, and my potentials are straight B's. All right, so how are you going to solve this one? What are you going to do? Okay, so remember, potential was basically the potential energy per unit charge. Okay, which means if I know the potential difference, I also know the potential energy difference. And if I know the potential energy difference, I know the change in kinetic energy by conservation of energy. And in this problem, we're going to go in the reverse order. Since I know the change in kinetic energy, I can find the change in potential energy, and therefore find the change in potential. Go ahead and try that. Okay, so to do it, let's go ahead and use our process. So I'm going to say K1 plus U1 equals K0 plus U0. That's my conservation of energy. All right. Now I stop, which means K1 is 0. Okay. And I'm trying to find the potential difference. Okay, so since I'm trying to find the potential difference, let's subtract the U0 over. I get U1 minus U0 equals K0. And now let's rewrite those with what we know their relationships. This is just the charge, Q, times V1 minus V0. Okay, and that equals 1/2 m V0 squared. Okay. And potential energy for a point charge, or for electric potential energy, is just the potential of the sources times the test charge. Okay, and now this is what we're looking for. This is delta V. So rewriting that over here, I'm going to say delta V is equal to m V0 squared over E, which is the charge of the electron. Okay, now that's a negative E. It's negative E, which it should be, because this is the potential difference it goes through. Final minus initial is negative. I went to lower potential. This is smaller, this is bigger, so small minus big is negative. So that's where that negative comes in the math. So if you plug in your numbers, you're going to get a negative 0.71 volts. Now we don't have a lot of intuition on volts yet. And especially in the case like this, stopping an electron, we don't do that a lot in our daily life. But just as a note, a battery, a regular AA battery, is about 1.5 volts. Okay, so this is about half of a AA battery to stop this electron. 50,000 or 500,000 meters per second sounds big, but it's actually not terribly big compared to how fast an electron could go. You can get them going at the speed of light nearly, because they're so small, such a small mass. So this is hard to assess, but we know it should be negative because we went to lower potential. All right, let's move on to the next problem, problem 35. Okay, problem 35. It's a fun one. You're probably like, didn't look fun to me, Dr. Hale. Okay, so we have a rod that is uniformly charged on one side with a positive charge, and then charged on the other side uniformly with the same size of charge but negative. And we're asking for the potential at that spot right there, a distance d above the midpoint of that rod, and this rod is of length L. Okay. Now technically we need to integrate that, because we could break up each of these halves into little point charges, so little dq's, and we'd integrate that. It'd be a little bit easier than if we did an electric field, because we don't care about direction, it's just distance. So, but it still wouldn't be the prettiest thing. But before we do, if you remember how we integrated continuous charge distributions for electric field, first thing we did was to look for symmetry. Okay? Now remember, the potential is not a vector, it just cares about size. So with that, thinking of symmetry in this problem, what is the potential at that dot? Okay, the answer is 0, because no matter what piece over here I have, it's going to create a potential, positive potential at that spot. But there, for every piece over here, there's a piece of equal size but opposite sign that's going to create the same negative amount over here. And so this is going to give a potential at that spot equal to 0 by symmetry. Okay. So again, this is critical to think about symmetry and noting that potentials are not vectors. It's only about size. Okay. So again, let's just to help out with that, let's suppose I take a little chunk here. Here's a little dq. Well, it's going to create a potential here of some amount and positive. Well, over here is the same size dq, only negative. And it's the same distance away, so it's going to create the same size of potential, only negative. And so those two would cancel. And I could repeat that process all along this positive bar. For every piece on this positive bar, there's a piece on the negative bar that creates the same size potential, only negative. Okay, moving on to our last problem, 43. Okay, go ahead and take a look at this problem. See if you can solve it. Okay, so here's the setup. All right, and we're asked if we know the velocity of this proton at point A, and it's moving between point A and point B, okay, what is its velocity at point B? How would we find that? Before we do the math, let's ask, do we know if it's going to speed up or slow down? We could see it's moving from a high potential to a low potential. All right? Well, what is the direction of the electric field along that path? Electric fields point from high to low. So the electric field is this way. All right? Now that we know the direction of the electric field, well, what do we know about positive charges in electric fields? Do they move along the electric field or against it? Positive charges move along the electric field. Think about this electric field is caused by some positive charge over here. Well, another positive charge will want to go away from it. So the positive charge wants to move along this electric field, which means if it is, it must be speeding up. So we know that it must be speeding up. Okay? And doing something like that is really valuable to make sure it's clear, and it helps to get you ready to solve the math. So that's the concept there, is we know it should be speeding up because it's following the electric field, because electric fields point towards lower potential. Okay, so with this in mind, this sounds like a conservation of energy problem. I know potentials. Potentials are related to potential energy, and potential energy is related to kinetic energy, and kinetic energy is the definition of energy of motion, which is velocity. So I can start out by saying KB plus UB equals KA plus UA. All right? And I want to find the velocity at point B. So solving for that, KB equals KA plus UA minus UB. All right? Now plugging in what we know these to be, this is a 1/2 m, and it's a proton, times VB squared equals 1/2 MP VA squared, plus, and potential energy is equal to the charge times the potential. So this would be E, that's the size of the charge of a proton, times, and I'm going to just factor it out right away, times VA minus VB. Okay. So again, potential energy of a charged particle is the size of the charge times the potential created by all the sources. Okay, let's simplify the solving for VB. I'm going to multiply everything by 2 and divide everything the mass of the proton. Gives me VA plus 2E over M, VA minus VB, and square root the whole thing, because it was squared, and then I square rooted the whole thing. And so now I can just plug in my numbers, noting that the charge of a proton is 1.6 times 10 to the negative 19. The mass of the proton is 1.67 times 10 to the negative 27. And I can read my potentials here. Potential at A is 30 volts. Potential at B is negative 10 volts. So VA minus VB is 30 minus a negative 10, which is 40. And then this is the given value of 50,000 meters per second. So when you plug that in, I get 101,000 meters per second, which is bigger, as we had deduced from our concepts. Okay, so I hope that these made some ideas clear about potentials, and I hope you practice with them thoroughly.